Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. I wish you have a very pleasant morning and serenity. Welcome to webinar desain series number 3, Dialog Eksplorasi Sains Data dan Informasi, entitled Simulating the Future, Multi-Agent System for Complex Socio-Environmental Dynamics, held by Research Center for Data and Information Science, National Research and Innovation Agency of Indonesia, BRIN, in Bandung, Indonesia, Wednesday, 15th April 2026. I'm Christine Widianingrum, and I will be served as the host today. It's an honor to me to inform you that among us here, we have distinguished Head of Research Organization for Electronic and Informatic BRIN, Professor Dr. Eng Budi Prawara, Distinguished Head of Research Center for Data and Information Science BRIN, Professor Dr. Esa Prakasa, MT, Distinguished Dr. Alexis Drogul, and Mr. Andrea Arisa, MN, as presenters, Distinguished Dr. Purnomo Husnul Hautimah as a moderator, Distinguished Researcher from Research Center for Data and Information Science BRIN, and all participants joining via Zoom and YouTube BRIN Indonesia. Well, ladies and gentlemen, please allow me to read the agenda for today's webinar. The first agenda is the opening session. Second will be presentation led by our moderator. Last but not least, there also be to the closing statement session. Distinguished ladies and gentlemen, please allow me to read the webinar guide. Please stay on mute while the presenter is speaking and use the raise hand feature or the chat box to ask questions. Participants are encouraged to rename themselves using the format name _ affiliation. Participants are welcome to use the provided virtual background. And please complete the attendance and feedback form via the link provided in the chat to quality for a certificate. 3 lucky winners will receive prize, which will be announced at the end of the webinar. Ladies and gentlemen, first agenda, opening remark by Head of Research Organization for Electronic and Informatic BRIN, Professor Dr. Eng Budi Prawara. To Professor Budi Prawara, the screen is yours.
Thank you, Mbak Christine. Assalamualaikum warahmatullahi wabarakatuh. Good morning and warm greetings to everyone. Distinguished speakers, Dr. Alexis Drogul, and our colleagues Andrea Rizal, also Dr. Esa Prakasa as Director Center for Data Science and Informations. Respected colleagues and all participants joining us today, it is a pleasure to welcome you to our webinar with the topic of simulating the future multi-agent system for complex socio-environmental dynamics, hosted by Research Center for Data Information Sciences under the Research Organization for Electronics and Informatics. We are gathered here to explore an approach that is increasingly essential in understanding today's world, multi-agent systems. Many of the challenges we face, particularly in socio-environmental domains, are inherently complex, involving multiple actors, interdependencies, and dynamics interactions. These challenges cannot be fully understood through linear models alone, and this is where agent-based modeling offers a powerful alternative. Today's webinar also introduce the Gamma platform, an open source platform for agent-based modeling and simulations. Gamma stands as a compelling example of how research outputs can evolve beyond academic publications into robust, usable tools that deliver real impact. through this platform, like Gamma, researchers and policymakers are able to simulate scenario, explore system behavior, and support more informed and evidence-based decision-making processes. We are honored to have Dr. Alexis Drogul with us this morning. He is the core developer of Gamma platform, who will present his work on modeling and simulating complex socio-environmental systems using multi-agent systems with a particular focus on the Gamma platform. His work illustrates how individual agents representing people, infrastructure, or environmental elements interact with dynamic environments to reproduce real-world complexity. Such simulations enable us to better understand system behavior, test alternative scenario, and inform policy design in areas such as urban planning, environmental management, and disaster response. We will also hear from Andrea, who will present a research project focused on disaster response management in Indonesia. His work centers on an evacuation route optimization system that integrates road networks, population data, and multi-hazard risk scores to identify and rank safe, efficient evacuation paths. These optimized routes are then embedded with an agent-based simulations to examine how different evacuation strategies performs under realistic conditions. Importantly, this work is not intended to predict exact outcomes, but to provide a structured foundation for discussion among stakeholders, supporting more informed and effective disaster response planning. I hope these sessions will not only enrich our understanding, but also inspire new ideas, collaborations, and innovations that bridge research and real-world applications. Thank you to our speakers, the organizing team, and all participants for being part of this webinar. I wish you a fruitful and engaging sessions. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Budi Prawara. Now we will take a photo session. Please to all participants to open your video camera and team will take a picture. Please, Mr. Dio.
Okay, I will now take the picture of slide 1 in 3, 2, 1. Okay. Now I will take a picture of the slide 2 in 3, 2, 1. Okay, now I will take the picture of slide 3 in 3, 2, 1. Now the last slide, I will take the picture in 3, 2, 1. Okay.
Okay, thank you very much, Mr. Dio. Thank you all participants. Ladies and gentlemen, next agenda are presentation for all speakers, led by Dr. Purnomo Husnul Khotimah. Before we begin, I will read the curriculum vitae of Dr. Husnul. Dr. Purnomo Husnul Khotimah is Senior Researcher, National Research and Innovation Agency, BRIN, specialization Medical Informatics, Data Science, and Spatio-Temporal Data Mining. Education background, PhD in Social Informatics, Kyoto University, Japan. Magister Teknik in Electrical Engineering, Bandung Institute of Technology, Indonesia. ST in Electrical Engineering, University of Indonesia. Professional experience, senior researcher at Research Center for Data and Information Science BRIN. At this epidemic modeling, developing deep learning framework for the detection and prediction of infectious diseases using multi-source data, sentiment and social mining, analyzing Indonesian consumer sentiment toward global trend using Twitter datasets, and spatio-temporal analysis, researching in the intersection of environmental factors and public health outcomes through large-scale data mining. Okay, this brings to Dr. Husnul. The screen is yours.
Okay, thank you for your kind introduction, Miss Christine. Okay, Bismillahirrahmanirrahim. Good morning, distinguished guests and speakers, colleagues and participants. In this session, we will have two presentations presented in sequential order and then followed by Q&A. The presentation will take the topic of simulating the future multi-agent system for complex dynamics. And for the first presentation, it is our great pleasure to have Dr. Alexis Drogul. Could you please show the CVs? Okay. Thank you. So, Dr. Drogul is currently the Director of Research at the Unit for Mathematical and Computer Modeling of Complex Systems, UMMISCO, within the Institut de Recherche pour le Développement, IRD in French. With a career spanning over 3 decades, he is widely recognized as a leading expert in artificial intelligence, particularly in the fields of multi-agent system and socio-environmental modeling. He earned both his master's and PhD in artificial intelligence from Université Pierre et Marie Curie in Paris, laying the foundation for a remarkable academic and research journey. Throughout his career, Dr. Drogul has held several prominent roles, including professor at Pierre and Marie Curie University and senior researcher at IRD, where he continues to contribute significantly to global research initiatives. He also served as co-director of the SCR-OSS laboratory. And Dr. Drogul is perhaps best known as the architect and lead developer of the Gamma platform, a powerful and widely used tool for agent-based modeling and simulation. His contributions include more than 200 high-impact publications, particularly in cognitive agent architectures and the modeling of complex urban and ecological systems. Beyond his research, Dr. Drogul has played a key role in fostering international scientific collaboration, especially between France and Southeast Asia, through his work as IRD representative in Vietnam and the Philippines. He also the founder of the Tam Dao Days Summer School, which have trained hundreds of researchers in social and environmental modeling. And today we are honored to have him share his insights and expertise with us. So please join me in warmly welcoming Dr. Alexis Drogul. Good morning, Doctor.
Yeah, good morning. Thank you very much for your very kind introduction. So should I
I
share?
heard that you are okay. So I heard you are in Vietnam now.
Yes. So I
Your
am in
position.
Vietnam. I am based in Vietnam, actually. I'm
Okay.
working in Vietnam. And I think we shared
Okay.
some
Okay.
common friends at Kyoto University, because I've been
Yes.
working for 1 year there in the social informatics laboratory with Professor Toru Ishida.
Oh,
But
yes.
it was a long time ago.
I have heard of him. Yes. Thank you, Doctor. I hope this webinar could also could be a good start for us, maybe for in how to say near future collaborations. So thank you, Doctor. So maybe we could start with the first presentation. So
Okay.
to Dr. Dragul, the screen is yours.
Okay, so I'm going to share. So can you see my screen right now?
Yes.
Yeah, perfect. So thank you so much for this very, very kind introduction. I didn't know exactly what to expect in terms of introduction, so I have a few slides introducing myself, but I will skip through them very quickly. First of all, I would like first to thank all the organizers for inviting me today, especially Andrea, because we met in not so long ago, actually, in Thailand, and it was really, really interesting work together. Of course, my participation today is intended to maybe serve as a beginning of fruitful collaborations, because it will be the first time for me to speak in front of an Indonesian audience. Okay, so I'm very honored to do this. So thanks a lot. And if you have, well, I will be happy to share some of my, let's say, knowledge, but also to answer your questions if you have any, even if they are related to your own research. Okay. So let's begin with what I'm going to talk about. So it's modeling and simulation of complex socio-environmental systems. And as has been mentioned before, I'm going to talk about mostly agent-based modeling and the Gamma platform, but not only. Okay, I will also have more general and maybe a little bit more theoretical findings in this presentation. So a little bit very, very quickly about myself. I began, actually, I did my PhD now more than 30 years ago in Paris. And I was at that time mostly working on AI and robotics. Okay. And it is through these double work on self-organization of robots and things like this that I began to discover modeling and simulation of complex systems. Okay, not only human system, but also animal societies, for example. And then that I began to slowly move from trying to build intelligent systems to trying to simulate intelligent systems. Okay. Existing intelligent systems, like, of course, human societies. In 2004, I moved actually to IRD. So sorry, there is a little glitch in the title. So I moved to IRD, and IRD, I will present it very quickly. It's an institute which is represented actually in Indonesia. Okay, we have a permanent representation there, and there are researchers. So it's a very clear possibility for collaboration again. And I've been working for IRD in Vietnam since 2007. Okay, so it's been now almost 20 years I'm working in Vietnam and with Vietnamese colleagues on different things. One of my main activity, I would say, is capacity building and building of structures that allow people to work together and that allow us to train Vietnamese researchers and students on new technologies for modeling and simulation of complex systems. Okay. So I will not spend too much time here. Just introduce IRD. So IRD, it's a French public institute. It's a French research institute that undertakes not only research, but also capacity building, so like training, in a field called sustainability science. So sustainability science, it's you probably heard about it. At least you heard about sustainable development and sustainable development goals. Okay, SDGs. So it's exactly aligned with these approaches, and the goal is really the goal of sustainability science. I will describe it a little bit later, but it's mainly to find ways to scientifically support sustainable development in all its very numerous dimensions. Okay. IRD is quite small compared to to the other French public research institutes because we have, let's say, around 850 researchers, so it's quite small. But there is one peculiarity, is that more than half of these researchers are permanently abroad. Okay, so they are permanent in other countries than France. Like me, for example, in Vietnam. Okay, so usually people stay between 3 to 6 years in countries, so they're not completely permanent. Okay, it depends really on the context and the projects, but it's for quite a long time. And actually, we come in support of colleagues in these different countries. So we are working, let's say, in what is called globally the global south, whatever that means, basically. But for example, in Asia, in Southeast Asia, we are mainly working in Vietnam, Laos, Cambodia, Thailand, Philippines, and Indonesia. Okay. So Indonesia is one of the targets, and I think that we have something like 5 permanent researchers there, not in computer science, not in AI, but why not? Maybe in the future, right? So if I wanted to define actually what sustainability science is, first of all, it's important to understand that it's an interdisciplinary research domain. So it's not attached to a specific domain. Okay, it doesn't belong to social sciences. It doesn't belong to engineering sciences or exact sciences. Okay. It's really something where we try to match and mix actually scientific domains and have them work together on very specific problems attached to sustainable development. So first of all, interdisciplinary. Second of all, we are very strongly linked in sustainability science with, let's say, interventions, applications, implementations. Okay, so it's clearly an applied research domain where what we want to tackle are problems found in society, and basically the interventions we are trying to support are interventions that foster prosperity, reduce poverty, and protect the environment at the same time. Okay, so clearly aligned with the SDGs. So if you take more formal definitions, like the one given by UNESCO in 2023, they say that actually it's a two-sided scientific domain. On one hand, it is the science about sustainability. So we try to understand in this domain how complex physical, biological, social systems function. Okay, how do they work? How can they maintain themselves? What could be their future, etc., etc. And at the same time, and sometimes in parallel, actually, and we really in an interconnected way, it is a science for sustainability, in which we not only try to understand, but we try to design policies. Okay, we try to design social, environmental transformations, and so provide tools, scientific tools, to do this. So that's the definition of UNESCO. And then you have well, it's not really a definition, but more a complement actually made by my own institute, IRD, in 2020, saying that one thing that characterizes sustainability science is the use of what we call transdisciplinary methodologies. So transdisciplinary methodologies, it's really about actually trying to go beyond scientific domains, or to go beyond researchers, etc., whenever we try to invent solutions, but also involve and mobilize stakeholders, okay? Mobilize communities, mobilize people who will be affected or who will be impacted by these solutions. So non-academic players, if you want to call them. And so trying to promote what in other domains you will call participatory science, for example, or things like this. Okay, so it's quite important to keep that in mind and to understand that actually all these landscape, so interdisciplinary, transdisciplinary, or participatory, if you want, and trying to design solutions, this landscape actually is important to understand why agent-based modeling has become a very important tool in this sustainability science domain. Okay, so as I said, we try to provide understanding, decision support, and stakeholder participation all at once in order to tackle very complex challenges. And I just gave some example. I have two more examples, or three more after that. But I mean, the kind of problems we are trying to tackle are, for example, improve the efficiency of water use, okay, or design new agricultural practices to help mitigate climate change, adapt to its impacts, preserve ecosystems, etc., etc. Build sustainable cities and communities, okay, or anticipate pandemics by understanding the interactions between environmental, human, and animal health, etc., etc. These are just examples. Okay, I will not detail them at all, but I just want to show you here that actually whenever we're talking about sustainable development problems, there is no way we can separate the social, environmental, economical, or let's say any other word in all domain. Okay, they are all connected. They are all interdependent. And these strong connections and interdependencies actually make them systems that require new technologies. So some of the technologies come from the digital world. And now, for example, we have AI gaining ground a lot in these applications. Some come from more analytical backgrounds like mathematics, okay? Some come from the social sciences. And you will see that basically agent-based modeling is a little bit at the confluence of all these inspirations, okay? All these different domains. So if I take more detail, but they are not really detailed, but basically if I spend a little bit more time on these different examples. So let's say for example that we want to work in a domain which is the spread of infectious diseases in a One Health approach. Okay, so we have components in such systems. We have a number of components that actually might be interesting to understand, to study, to represent somewhere, and for which maybe we need to understand their evolution in the future if we want to prevent the spread of diseases. So among these components, we have things at very different scales. So we have, for example, pathogens, okay, like bacteria or viruses, human behavior, networks, okay, at different scales of social contacts, healthcare systems, public health interventions, but also the soil health, for example, etc., etc. So we have a number of completely different components. And we know these components, in a way or another, are interacting. Okay, they are interacting. So whenever a farmer changes practices, it will affect the health of the soil, which may affect how bacteria, but also antibacteria drugs are, I don't know, for example, washed in the environment, in the rivers, etc., etc. So everything is connected in these systems whenever we try to find solutions, okay, to maybe prevent the spread of a disease. And the different challenges we might have in such a very big domain like One Health are, of course, to predict outbreaks, okay, but also to control them, to develop effective public health interventions, and maybe it can be also to develop simple behaviors, okay, so to promote simple behaviors, to give incentives to people to not do this or do this in favor of other behaviors. So we to prevent actually it's like during the COVID-19 epidemics, okay, or pandemics. Actually, a lot of interventions were at the policy level, like vaccination, etc. But you could also, and you had a number of more behavioral advices actually provided to people, okay, like wearing a mask or keeping some social distance, etc. So all of these things, whenever we are working on limiting the spread of infectious diseases, we can also intervene at very different scales. These, and it's a very closely related domain. These can be also found, for example, in whenever we want to fight antimicrobial resistance, okay, AMR, which is a very big subject everywhere now in the world. Again, we have pathogens, but we have also drugs themselves. Okay, we have farming systems, healthcare systems, food systems, which somehow are connected and may play a role in these different resistances. And the goal, the challenges, the things we would like to do are to predict the resistance, okay. To control also, it's maybe the prescription of drugs by doctors, etc. Changing people's habits, developing new regulations, etc., etc. Okay, so again, here we are facing a system where the social, environmental, economical worlds are completely connected, and there is probably no solution that can be only related to one of these domains. Okay, and we know that intervening or having an impact on one of these domains may affect the others very deeply. Another completely different type of applications I've been working on, for example, is plastic leakage and aquatic pollution. Again, the key components we have here, of course, we have a lot of things related to chemistry. Okay, so how does plastic degrade in water and how does it affect marine life, etc., etc. Okay, so chemistry, biology, of course, it is extremely important to understand what's happening here. But again, if we want to have an impact, the impact will probably not be in at least not immediately in, I don't know, building better plastics that degrade less in water, or finding a magical way for turtles and fishes not to eat plastic molecules. Okay, but we know actually that plastic is produced by humans. Okay, it's not some kind of natural thing. It has been completely produced by human, and basically the only leverage we have right now is to either stop the production or decrease the production of plastics, so make a more rational use of them, and it means also changing people's behavior. Okay, now. I don't know what's the state of this in Indonesia, but for example, in Vietnam, when I go to the market and I do my shopping, food shopping or whatever, it's quite usual that I come back home with 10 to 15 plastic bags, which are only one use, okay, unique use, and I will never reuse them probably, and they end up in the trash and they end up somewhere, and basically. You wonder how, of course, we individually we need to change this, but we need also to invent incentives, other solutions, etc., and to test them in advance to understand whether or not it's worth it, okay, to change the behavior of people. We did change the fact that we produce more and more plastic every year if we don't have plastic bags in the market. So, and all these things are very tightly connected again. And of course, the challenge is controlling the production, preventing leakages, developing effective policies, etc. So what we see is that these systems are so complex that whenever you touch something, you will have an impact on the other sides. And the only way we can talk about them, and actually it was very obvious when COVID-19 started, right? That all what people were talking about were models. Okay. We were talking about models. Look at the state of the worldwide discussions on climate change. Whatever we're talking about are models, predictions of the future of the systems we are living in. But basically, now models are becoming more and more prominent, more and more popular also, because people understand now what a model is, more or less, okay? And whenever we want to imagine policies, which is one side of sustainability science, we need to have models to understand how these policies will or will not change or, I don't know, solve a challenge or solve an issue we have identified. So what we might call sustainable management, okay? As soon as we have something related to sustainability, it means we are talking about the future, okay? Because sustainability is really about trying to make something that will be still relevant in the future. And when we talk about the future, we need models. Can be different techniques, and I don't care about the technologies right now, but we need models at some point to be able to support our thoughts. Models can be a number of different things, okay? And again, to be completely clear on this, for me, a model is a simplified representation of a system that will help us or others answering questions about the system, okay? So it can be anything. And of course, we are going to talk because of computational power, because of the very interesting possibilities they offer. We are mostly going to talk about computer models today. And I'm going to talk about computer models. But basically, computer models are just, if you take this definition, they are just models that take computer programs as the main representation. Okay, so the representation is a computer program. So we have computer programs that we call models that we run, and these executions will be called simulations, okay? We run them, we simulate them in order to solve our issues or to maybe to predict things or whatever. So what is important here to understand is that a model is a representation of a real system, but it's another discussion. Real systems don't really exist in reality. So they are also, their boundaries actually are created by scientists usually. Okay, they decide that this system is interesting, like for example, the system of plastic odyssey in the society and the environment or whatever. It's a system. But we create a simplified representation because we simplify things because there would be no point in building something as complex as the world, okay? Because this is precisely why we want to have models, is to simplify things, to be able to run different scenarios, for example. And another very important thing is that every time we build a model to answer a question, or sometimes one or two or three questions at the same time, okay? But there are questions behind. So we don't build models just for the sake of it. We don't have models of society or models of traffic or models of plastic leakage. Okay, it doesn't mean anything. We have models that help us answer a question regarding traffic or regarding plastic leakage or whatever. So as I said, computer models are models actually that use computer programs as a representation. And whenever we execute them, whenever we run them, these programs, okay, we call them in this domain simulations. So simulations are simply the execution of a computer model, right? So I will not go into details, but basically these simulations, since they represent one execution of the model, of course, they can have different inputs, okay? And then they might have different inputs. And these inputs, these input variables or input data, whatever you call them, they will represent scenarios. Okay, they will represent scenarios in which we try to see how the model reacts to some new inputs of data or hypothesis we might have, and we will see some examples of this later. So simulations, they are used for many different things. Well, you probably use simulations a lot on your phone, for example. Okay, because there are a lot of games, and this is probably, for the moment, the main economic output of simulations. Okay, a lot of games actually are relying on simulations. When you, I don't know, when you play on farm sim or things like this, actually you are simulating things. So it's not a scientific model, it's not a scientific simulations, but basically it's the same process. Okay. More seriously, it's used a lot for visualization, understanding what's happening, okay? Training, of course, because sometimes you can't train people on real machines or real systems. You have to use simulations, and this is where, for example, we are going to find virtual reality, okay, systems that represent with great details something that we don't want people to play with. Like, for example, if you are a pilot in a plane, okay, we don't want you to play with a plane. So you are going to play on a simulator first, and you acquire experience on the simulators. Control, forecasting, decision support, evaluation of different solutions. All of these are valid uses of simulation. And we use simulation for very different purposes. And we use simulation so much that now in many domains, it has replaced experiments. Okay, so sometimes it replaces experiments because we have no choice. Like, for example, nuclear power, okay, or we are not going to test, well, actually, a lot of countries did, including France, unfortunately, but testing nuclear bombs, okay, it's an environmental catastrophe, and normally we don't do it anymore, okay, for obvious reasons. So here we rely completely on simulations. There are things that we can't reproduce. So, for example, if you want to study how earthquakes affect a city, we can't reproduce an earthquake easily. Okay, and we are not going to, actually. We don't want to put people in danger just because we want to have some scientific data, right? So we need simulations here, and we need to have simulations. And even if we don't take some dramatic things like earthquakes or bombing or whatever, as soon as you play a little bit with human beings, we can't play with people, okay? We are not going to test new behaviors or to test new things on people. It's just ethical questions. So at some point, for example, let's say something very simple, you want to change a little bit the traffic logic in a city, okay? You are not going to experiment day after day with new directions for streets or things like this. You will want actually to have a model and a simulation that provides you with some idea of what might happen if you change the direction of a lane, or if you cut a street, or if you open a new one, or whatever. But you are not going to experiment on people, because actually it's just unethical. And the other problem with human beings is that they learn things. Okay, so if one day I don't know, you cut a road, people will adapt to it, and they will very quickly adapt. And basically, you cannot reproduce. So you can not have a scientific or experimental approach to these kind of problems, because you just can't reproduce it. People will have learned from yesterday or the 2 days before. Okay, so they will not be the same. They will not have the same behaviors. So whenever we deal with social facts, and it is the case in almost all sustainability problems, simulations become absolutely necessary. And of course, the simulation of dynamic things, simulation of the evolution of societies, simulation of what people do, what they learn, how they change, etc. So to study this, actually dynamic models and simulations, they have a very long history. Okay, it has become, well, let's say it has begun like 300 years ago, mostly with differential equations. Okay. But very quickly in the 20th century, with a number of things we are still using, okay, like stochastic processes, game theory, system dynamics, etc., etc. And with the advent of AI and all the different AI chapels, okay, in the 50s and 60s in the US and worldwide, we have things that have popped up like artificial intelligence, of course, but also cellular automata, uh, object-based modeling, okay, multi-agent systems that was mentioned before. So a number of things that basically belong to the same sphere of combination of artificial intelligence, knowledge representation, and software engineering. Okay, so this kind of combination of things. Object-based modeling is the best example. It has become first, you know that the first object-based language was called Simula. Okay, so it was really, it was before C++, before Smalltalk, before Java, etc. Simula, and it has been designed for building models and simulations. Okay. So it's a very, very interesting approach. And these combination of approaches have given birth actually to what I am talking about today is mostly agent-based models, which is a sum of different influences and a number of different techniques as well. So it's not only one platform or technique that is being used. If you take a look at all these different domains, actually, the question is which modeling methods can be used to address the sustainability of these complex systems. Okay. So what can I use if I want to represent the evolution of a system, I don't know, spread of a disease, if I want to test policies on this, etc., etc. What we want in sustainability science are models that can represent, for example, emergent dynamics. So things we don't know before, things we don't put in the model, but things that pop up, okay, they appear. Let's take a very simple example. You are in charge of modeling the traffic in a city and finding good things. You will face a number of emergent dynamics, like, for example, traffic congestions. Okay, traffic jams. Actually, nobody wants them. They are not here by design. Nobody wants traffic jams. Okay, and I think for example, in Jakarta, it's a terrible problem. But in Hanoi too, in Ho Chi Minh City too, in Bangkok too, etc. All Southeast Asia is more or less affected by this plague, at least the big cities. And this is something nobody wants. Okay, you don't design a car and you don't design something that should make you go and drive faster to obtain congestions. So congestions and traffic jams are really emergent dynamics. Okay. And it's a very simple example, of course. There are many others. But it's interesting because it has also emergent properties. Okay, you don't study traffic jams like you study cars or people. So that's the first thing. We want to be able to represent these dynamics because they represent, so for example, sometimes things that we don't want or things that we want, but we don't know how to design. Okay. We want to explore also what if scenarios. So what if scenarios are scenarios where actually we change things in the model. So we have the reality, we try to represent it as much as we can with high fidelity, let's say, like the digital twins, okay, approaches. But we change something. At some point, we twist something. Okay, what happens? This is what we call what-if scenarios. Okay, what happens when we do this? What happens when we do that? What happens when? And you try, of course, to have this a little bit more systematic, a little bit so to explore things. Okay, and that's why I presented this figure. Is that more and more we are moving from the very classical use of models and simulations, which are forecasting or backcasting. Okay, something you know actually, for example, in weather models. Okay, that's forecasting. You look at your application, you have a model telling you that it's going to rain in 2 hours. That's forecasting. And it's a very classical use. But we move more and more in sustainability science from these uses to what I call here exploration of models, exploration of scenarios, okay, where we try to represent plausible pathways of the system. And we try to understand when we disturb the system, when we change things, what happens, okay? So a number of what-if scenarios that we try to explore in a quite systematic way. And for that, we need experimental support. Okay, we need to have systems that provide us some support to do this. It cannot be done only by hand or by people, but more and more by machines themselves. Okay, I will skip this because basically it's more or less what I said already. Okay, the thing is, sustainability science, like other applied interdisciplinary domains, needs actually to be able to rely on new technologies for supporting different scales, different viewpoints, etc. The question of viewpoints is very important because, for example, if you take again a very simple example like sustainable forest management. Okay, if we take the forest as an object, and if we look at all the different viewpoints we can have on this object, actually there are hundreds of viewpoints, thousands. Okay, all the people that in a way or another interact with the forest will have a different viewpoint. And when we talk about sustainability, we need first to understand what it means for these different people. And sometimes it can be completely different. So for example, if we have people belonging to the wood industry, they will see the forest as a source of supply of good quality material. Okay. If we look at loggers, of course, for them it would be the interest of the forest is to provide enough trees at low costs. Okay, they don't have to invest too much. If we look at consumers, they will want affordable, I don't know, I just put examples, but affordable furnitures, okay? Or maybe just a place to wander and to go during weekends with children, okay? A local NGO will want maybe, local NGO working on social inequalities, for example, will want maybe that all communities have the same access to the resources of the forest. Environmental NGO might be in complete contradiction with that and say, okay, we want to protect these fragile ecosystems, so not a lot of accesses, etc., etc. Okay, I will not list everything, but we have so many different viewpoints, and all of them actually capture one part of why the system is important to society. So we need approaches that can embrace not only these different viewpoints, okay, which is not too complicated, but also embrace their heterogeneity and interactions. Okay, because sometimes people will have the same viewpoints, but they will need to negotiate. They will need to find a pathway, a common pathway, okay, to determine what the forest will be in 15 years or 20 years or 30 years. And for that, we need to make them talk together and we need to represent the viewpoints in the system. So the only approach so far, there might be new ones in the coming future, but the only approach so far that allows to represent these heterogeneities and interactions between different sources of knowledge is agent-based modeling. Okay. And it works, agent-based modeling, because actually it's not a very constrained technology. So basically you have a lot of freedom in this. What is it? Very simply, you take a kind of individual perspective here. Okay, so we recreate artificial worlds, okay, by recreating artificial agents. So the first thing is to decompose worlds into what we call agents, and agents can be anything. It can be people, they can be groups of people, they can be animals, they can be whatever you want. Okay, it's really what is relevant to the question you are asking to the system. So we obtain artificial agents. These artificial agents, they are populating virtual environments virtual worlds, or whatever you call them. So it can be a representation of a space with its properties, dynamics, etc. And these agents, we provide them with what we call attributes, behaviors, rules, whatever you want to call it, that allow them to change their state and change the state of the others. Okay. And so it can be discussion as well. It can be message passing. It can be different things. So if I take a extremely simple way of representing things, let's say I'm interested in the outcome of a football match by children on the beach. Okay, so here I will have the system, and my system is simply the beach and the children, etc. Nothing more actually. In an agent-based modeling approach, I will decompose the system into children and the beach itself, which is environment. Okay, so all of them will be represented by computer programs that I call agents. And these agents, I will give them some possibilities. So maybe, for example, one agent will have, or the agents will have some attributes. They will have a location in the world, and this location, they can change it, okay, etc., etc. Once I have all these different agents programmed and maybe tested for good interactions between them, I gather them together, and I run everything on the computer. And this is actually a new world, okay? I'm recreating a world, a virtual world. So it's exactly like a digital twin, okay? Or the same kind of actually of approach. And what is interesting for me is that this virtual world, I completely master it. I master everything. I can change the rules. I can change the weather. I can change the speed of the players if I'm interested in players. It's a miniature laboratory. Okay, so I have all the freedom I want to explore as many scenarios as I want. And this is extremely powerful when we come to studying socio-environmental systems, with, of course, the only issue that we want to have the most faithful models as possible, because we want to have systems and models that react the same way the real system will react in some situations. Okay, again, here, two properties of agent-based models. One is that they follow a bottom-up approach. So what we call here, we are belonging actually to the generative approaches that you can find in computer science. What we are writing at the thing, everything at the micro level. We are writing behaviors, we are writing interactions, we are writing message passing, we are defining the environment, using databases to describe everything, etc. And what we obtain, we generate outcomes during simulations at different macro levels. Okay, so when we visualize things, when we observe things, it will be at different levels. So I'm not interested in looking at one agent behaving. I'm interested in what they are doing together and what they are producing together. I already said it, but I want to mention it again. An agent can represent any object or actor of the system to model at any level of abstraction. Okay. It's important because it will determine also the kind of platform and technology we can't use or we want to use whenever we want to build some specific models. But it can be one people, it can be a group of people, it can be a crowd of people. So it really depends on the question you have. And for that, for example, if I take One Health model, okay, like the one, agents can be anything. They can be patients, doctors, researchers, households, authorities, industrials, animals, plants, blah, 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 food, molecules. We can even go to very, very, very specific things. Because, well, actually, we can build agent-based models with all these different components because basically the questions we have, if you remember them, are very diverse. Okay. And so usually the models we are building remain at one level of abstraction. So for example, if we have patients, we'll have doctors and researchers, and we play with these different actors. if we want to understand how the transmission of drug resistance happens between people, but we can also have different levels of abstraction at the same time in the same model. Okay, so on one hand, the dynamic of the disease itself and the dynamic of people. Okay, and this is important because agent-based modeling has become now one of the most prominent ways of building integrated models. We integrate a number of knowledge in them. So how does it work when you want to define something, when you want to have the kind of life cycle of ABM, okay, you want to build an agent-based model. First step, I already told it, is to define the modeling questions, okay? And then we have something that more or less follows for those of you who come from computer science and knows about object-oriented analysis and modeling and programming. We more or less follow the same kind of dynamic, the same kind of process. So we identify, decompose the system into different entities. These entities become agents. We provide them with attributes, dynamics, interactions. Then we implement them in a computer platform, language, whatever. And then, this is now specific to modeling and simulation, we have the simulation part, experimental part, where we conduct sensitivity analysis, calibration, validation of the model to make sure that we are effectively reflecting on what happens in, at least in some parts of reality, and interpret, exploit the model. Okay, and this is actually something which is more related to people in, well, it's more the researchers and scientists here, but actually not only, because this is where we are going to apply the model as well. Okay. And sometimes applying the model can be used, it can be used for decision support or whatever. So yes, there are something I did not, so we have visualization, interaction, publication by scientists. It's quite important, okay. And of course, a number of loops here with, at the heart of everything, the collection of relevant data. And this is something I want to emphasize a little bit, is that agent-based models are data-driven models. They are data-intensive models. Okay, we need a lot of data. And you will see later that it's a case in almost all activities. So it can be something complicated sometimes, because when you don't have enough data to build a realistic model, okay, sometimes agent-based modeling is not the right approach if you don't have data at all, or if you don't have enough data, only hypothesis, for example. Okay, so defining the modeling question, I will go through these because probably you already all know what I'm talking about here. But the modeling question is, if I take again my antimicrobial resistance model, we can answer a number of things. Okay, we can address a number of challenges, and the modeling question itself will determine what kind of agents I have. So it can be, what will be the impact of reducing the use of antibiotics in hospitals? Does the presence of animals increase or decrease AMR in a household? How is it transmitted in human alimentation? How does it propagate at large scales, etc., etc.? Okay, these are all valid questions and interesting for a number of authorities, stakeholders, people, hospitals, doctors, etc. And they will. So it might seem obvious for you because maybe you are already working on some of these questions, etc. But actually, sometimes it's not so obvious. Okay, sometimes when I work with, for example, municipalities in Vietnam, sometimes people they come to us and they say, okay, we want a model of the city. But what is it? I mean, I don't know what a model of a city is. Okay. I don't know what the model of antimicrobial resistance is. Okay, there is no such model in the world. The only thing I can do is to build some program that I will call model that answers some specific questions. Okay, but again, it's important to very early determine the question you want to address with your model or in your model. Actually what I was going to say about the city, but a urban design model actually could be answering to many different things. Consequences of mixing usages on the well-being of people, okay? Crossing infrastructures to preserve the life and security of pedestrians, relation between density, traffic, and air pollution, where to build parking lots. Okay, this is something so important now in our cities, etc., etc. Okay, and it can be also very commercial things like how and where to place advertising panels to maximize their view by people. Okay. So again, very, very diverse questions can be addressed by models. Okay. Once you have a very clear question, which is usually absolutely not the case after a first meeting, so you have a loop of things, okay, and a loop of discussions between stakeholders, modelers, scientists, etc. But let's say you have a very precise questions. The goal is, with respect to that question, how do I decompose my system? And here, with agents at completely different scale, depending on the questions. For example, if I'm interested in the impact of the food choices, the food habits of people on propagation of antimicrobial resistance, okay, probably my agents will be people, okay, might be the industrials producing the food, okay. Maybe there might be also farmers and farming systems here, the one that produce actually the elements of what transformed food will provide to people, etc. So depending on the question, I might have very different actors popping in and agents popping in, and of course, different kind of scientific domains involved. Okay. Again, in a city, it's the same kind of vehicles, groups, traffic lights. Actually, traffic lights can be agents if you want to work on autonomous systems or smart cities or whatever. Buildings, infrastructures, networks, all of these can become actually agents in an agent-based model. Once these agents are defined, comes the more implementation part, so the one which requires the use of languages or platforms, okay, to build things. So I will go very quickly. Definition of the agents. It can take, so you are used to UML, things like this. Okay, usually we use the same in agent-based modeling, almost. So there are some very specific things like RD, but again, we use very really closely related systems. When it comes to the implementation, actually, we normally have a mixture of very lot of different things in a model. We have, it's very detailed models, okay? Complex pieces of software. So complex data sets, we have geographical information, usually when we're talking about people and cities and things like this. We may have qualitative and quantitative surveys results. We may have demographical and statistical data available. And all these different data sets need to be integrated in a way or another. Okay, and for that, actually, you need to rely on software that provides such integration easily. That's the first point. Second point is you saw before, we need to produce, we need to be able to run experiments, to run simulations, to change scenarios, etc., etc. And for that, again, well, actually, it's like for any kind of science. If you want to conduct experiments, you need to have laboratories, okay, to be able to control things. And here, a platform like Gamma, so Gamma is, which I introduced actually here, is precisely built for that. It provides the integration that a lot of people need actually to build integrated models. And at the same time, experimental tools that allow people to run simulations in a controlled way. Okay, not only by hand, they can do it by hand actually, but not only by hand, but in a very controlled way. So That's the two first things. Second thing is that people come from different backgrounds. Okay, so usually around the table when we tackling sustainability problems, we have mathematicians, we have computer scientists, we have physicians, we have biologists, chemists, etc., etc. So a number of different disciplines usually are involved. And all of these disciplines, many of these disciplines, not all, but many, have traditions. They have different paradigms. Okay, they're using different models and different paradigms. And a platform like Gamma allows to integrate different paradigms. So for example, you can have physical models, you can have mathematical models based on differential equations, for example. You can have object-based model, you can have agent-based models, etc. And they all operating on the same data settings. And we provide ways actually. So it's, of course, it's not magical. So you have to write things. But we provide support to be able to combine all of this. So if you want to combine, for instance, an equation-based model of fluid dynamics representing some kind of flooding, and the behavior of people which would try to escape the flooding, you can do it in Gamma. Okay, and this is extremely useful when it comes to building integrated models. So it's free, it's open source. So you can also adapt it to your needs. I don't say it's easy, again, because it's an old software with a lot of iterations and a lot of actually lines of code, but it's possible to build specialized plugins for it. Okay, and if you want to integrate very specific data or very specific ways of representing your knowledge, it's mainly a Vietnamese, French cooperation, but we have people coming from US and Netherlands working with us. And maybe tomorrow people from Indonesia, I don't know. It's quite a comprehensive ABM platform. So again, it's a platform in which we try to do everything. Well, not to do everything, but to provide support for a lot of tasks. So it's very user-friendly. You can, in a matter of seconds, actually, you can write a model and run it and visualize it, which is a very important thing to do. So you can build, simulate, visualize, analyze things. It supports the development of quite complex models because you have all the power of object-oriented programming behind, actually. And you can integrate spatial modeling, GIS functionalities, etc. It's developed in Java, so it's open source, easy to extend, quite easy to extend. Okay, and it provides also quite flexible, actually, modeling language, which is called GAML, which allows actually to manipulate high-level abstractions rather than having to recode and rewrite everything by hand every time you make a new simulation. All right. Okay, so the number of, to be honest, the number of users, we don't know exactly, okay, because it's open source and people can actually download it and build it on their own computer. So maybe there are more, maybe there are less, okay, but more or less, if we take into account a number of other indicators, we are around 9,000 users. So it's very few compared to the, let's say, global market of computer science, but it's quite a lot when you think about how many people use modeling and advanced modeling and simulation tools. Okay, so it's a niche market, of course. And we are not here to sell something. So, well, in any case, it's not really a market per se. Okay, so that's numbers. So what do we do in Gamma? So very simple example. You will have a very good example coming just after me, actually, by Andrea. So for example, Escape was a project where we explored evacuation strategies in different scenarios of a dam breaking in Vietnam and in a very specific district of Hanoi. Okay. So basically, it's a scenario where we say, okay, the Hoabing Dam is breaking here, and we have a model for this. What happens if this dam is breaking? We have a model of what happens, and we know that actually people have 30 minutes to evacuate one of the most densely populated districts of Hanoi. Okay, with only three possibilities to escape, etc. And so we tried many different things. The goal here is not to predict the future because we don't know if this dam will break or not. Okay, but it's a scenario, and in this scenario there are many different branches. We can say, okay, how do we inform people? Depending on how we inform them, they might have very different behaviors. Okay. Who do we inform if we decide to inform them, if we can inform them? Who do we inform first? Do we inform randomly, 10% only? If we inform everyone, will there be a risk of emergent behavior like traffic jams, trying to escape, people trying to escape, etc.? So all these questions can be answered in a model like this. Of course, it will never be reality, and probably reality will be completely different when it happens. And I hope it will never happen. But here we have ideas, different scenarios, and things not to do maybe at all, or things that could be tested or tried depending on the day it happens, the hour it happens, at night or during the day, etc. Okay. So even if it doesn't provide solutions, it provides think about solutions. Okay, about all the possible cases, all what everything that can happen. Another example is something again in Hanoi. It's called Hoan Kiem Air actually, and it was the idea of linking air pollution with traffic and the new policies in Hanoi of building pedestrian zones in the city center. Okay. And so the goal here is to integrate different things. So we integrate, of course, the traffic. So there is a model of traffic with origin, destination by people, etc., etc. And then you have a model of emission. So each car, each motorbike is emitting some pollutants. Okay, so here it's mostly PM 2.5 we are interested in. And then a model of diffusion, which depends on the humidity, wind, conditions actually in the city. And we try to understand the impact after that. We try to represent, sorry, the impact. Okay, impact of this pollution on people based on the literature. So it's long-term pollution, long-term impacts on health or things like this. And the interest of this kind of model is that you can change everything. Once you have this virtual world, actually you can change whatever you want. You can increase or decrease the density of traffic. You can change the mix of traffic, cars, motorbikes, etc., etc. You can introduce electric vehicles. Does it change something? You can change the pedestrian zones. Okay, how do they create the conditions for better air or not? Because sometimes if you put too many pedestrian zones, you create traffic jams, okay, and congestions in other parts of the city. So in ONKM Air, we tested many different things. Okay, we tested different configurations, and we worked actually with Hanoi municipality to test in advance before doing it. Actually, test in advance the impact of different scenarios of traffic. I don't know if I have time again or if it's.
Yes, there's still
Yeah.
time.
Okay,
Dr.
cool. So again, these are examples. You can, and I hope actually that you can relate these examples to things you are already working on or things you would like to study or to work on, etc. I have actually, if you have questions, I have thousands of other examples, but I will not provide them here. I would like just to finish on 4 challenges because you are all, most of you, I guess, are scientists. maybe we are going to work together in the future. Okay. And actually, scientists, when they want to work together, usually they work together on challenges. Okay. Open things. You are not wanting to work on things we already know and we already completely master. The interesting things are the things we don't know and we don't master. Okay. And for that, I will finish on 4 challenges of agent-based modeling. These are my views. It doesn't mean they are the only ones, and it doesn't mean they are super interesting. Okay, at least I'm interested in them, and maybe I could be interested in collaborating with people to tackle some of them. So these 4 challenges are the following ones. First of all, improve stakeholders' involvement in decision making. Okay, so how do we combine these models with participatory methods to make sure that all the viewpoints are represented, that actually what we are building are inclusive models, okay? Where inclusivity means we try to take into account as many viewpoints as possible to have interesting scenarios or pathways. Second challenge is the confidence in models. Confidence in models, it's a very old topic. Okay. And basically, you probably all know the very famous sentence. Now I don't remember exactly who said it, but basically, which means that all models are false, okay, but some are useful. But if you want models to be useful, you need to have people being confident in their use. Okay, they need actually to trust the models, and for that it's not so easy because, well, I will come to this later, but building confidence in models means either you provide ways for people to build them very easily and to experiment them, etc., or you allow them to look at how they're built. And in that case, it's more a question of education in using models. Okay. Education in understanding what a model can do and can't do. Third challenge, offering a semantic support for reusing and coupling models. That's a big challenge, but mostly for software engineers, okay? In that we are producing thousands, millions of models every day, okay? And people, actually, a lot of scientists are building models of different things. All these models answer to different questions. So they cannot be easily connected, okay? Because sometimes they answer completely different questions. But we don't have very good ways to reuse them and couple them. And that's a real issue because we don't want, so even though we have things like Gamma, which basically provide some kind of shared facilities for building models, etc., and some reusable components that you will find in every model, it's not sufficient. Okay, when we want to tackle very complex systems, it's not sufficient, and we don't want to rewrite everything by hand every time because it's very complex. And then the fourth challenge is addressing scalability issues. Scalability issues, actually, it's when I told you that actually agent-based models are data-driven, data-intensive models, it means that usually we are looking at situations or real models with at small scales, okay, not big scales, not the scale of a nation, of a whole city or whatever. And when we look at the whole city, we usually reduce things. So why do we reduce? There is on one hand the problem of computational power. So if you have millions of agents, you need to have very powerful computers, and sometimes it's not. It's just not available right now, not yet. And on the other hand, it's also the problem of understanding what's happening. Okay. If you have millions of things interacting on your computer, probably you will very easily and very quickly lose track of what's happening. And this is quite a challenge, for example, to have systems that summarize what's happening in the simulation. And for that, AI can be very, very useful, actually, all the new AI techniques. So that's the 4 challenges. Maybe I will simply talk about the first one, but of course, I'm happy to take questions on the 3 other ones. First one is combining models and participatory methods to improve stakeholders' involvement in decision making, which is, let's say, the 3rd pillar of sustainability science. Okay. And we have to face something that models, scientific models, are mostly produced by scientists for scientists. Okay. And whenever they have outcomes that are visible outside scientific publications, it takes the form of more or less scientific articles or reports for DESAIN, for example, the IPCC reports. Okay. It's difficult to involve people, general public, for example, in such models or in building more robust models, etc., etc. And the thing is that when we think about sustainability, when we think about sustainable solutions, if we don't involve and mobilize people from the beginning in the design of these solutions, they will probably not adhere to it. They will probably not follow it. And maybe actually the solutions, even though they are ideal in the model, will fail because people just don't follow them. Okay, they are not. They did not participate to their design. Okay, so that's something which is quite, of course, important and crucial if we want to have interesting outcomes from this sustainability science domain. And what is interesting here is that ABM, agent-based modeling, provides actually quite a natural advantage here. Because agents, as I said, they can be anything. Okay, they can be absolutely anything. They can be neural networks, they can be rule-based systems, they can be computer programs, databases, whatever. They can even be people. Okay, so actually they can be puppets that people are playing in a simulation in real time, exactly like, and I come back to this, when you're playing a sim farm on your computer. You are one of the agents of the simulation. Okay, so usually you are the only one playing, but it can be a multiplayer system, and when suddenly you become a number of, and you have non-player characters, and you have different things, and so ABM, it's a very natural support for participatory approaches. And this is, so in Gamma, for example, we offer a number of tools to allow people to take the role of agents, okay, in multi-agent systems, in agent-based models. People can play the role of course, you need to program it. Of course, you need to plan it. It's not so easy. It doesn't come out of the box like this, but all the tools are here. And actually, it's a very powerful way of involving people to let them play their role or maybe play the role of others in an agent-based model of their community, for example, or the development of their neighborhood or whatever. So I already said it. We experimented with Gamma, for example, a number of different devices, physical devices, where you have people playing with different physical models, actually, of a city, of the evolution of things, etc. So we offer support for this, and of course, there are a number of other technologies that are available to do it. But what's must be kept in mind is that in agent-based modeling, it's quite natural to do it. It's not, you could not do it in with an equation-based model, okay? Because basically you don't have people there, okay? They can't play any role. But if you have models with people, it's very easy to make some of these people be played by humans. And so maybe taking decisions or whatever. And you can even go a little bit further, and this is what we are doing right now in Vietnam, by linking Gamma or these kind of platforms to advanced technologies like virtual reality. Okay. So in order not only to have people play a role and in a very, let's say, institutional way, but also have people mobilize emotions. Okay. Be immersed in something. Mobilize the same kind of interactions they are using when they are in real social life, etc. Okay, so this is what we are doing in a project called Simple. And this project is actually interesting and might be of interest to you because we are, it will come very soon. And of course, I will share the information. We are organizing a contest next year, next university year, to have groups of students, professors, researchers providing subjects for this simple project, subjects of models they would like to represent on sustainable development issues and basically ideas, pitches of games or activities in virtual reality that could be linked with this model to involve people better. Okay, so it's a contest. You have the address of the simple project here, the QR code actually, and please feel free also to send me a mail if you're interested. But basically, we are exploring a lot of different technologies combined with agent-based models. And agent-based models work very well for supporting these approaches. Okay. All right. So maybe if it's okay, I will skip this part because I think I've been quite long actually. You tell me that I have time, but I think I've been a little bit too long. No?
Okay, maybe 10 more
Yeah.
minutes.
Oh, okay. Well, I already talked about the challenges. The one on confidence speaks for openness. Okay, so it's for me, it's absolutely crucial that the tools we use and manipulate are as much open as possible. It's not easy. It's not easy for many different reasons. Building open source platform now is much easier than it has ever been, so it's okay. What is not completely easy is the data, the openness of data. Okay. So for example, in Vietnam, I don't know how it's what's the state of it in Indonesia, but sometimes people have a hard time building agent-based models because they simply don't have access easily to open data. They have access to data which remains either private or not usable or not shareable. Okay. It can be public or private data. And of course, this is quite an issue if we want to improve the reproducibility of models, the confidence of stakeholders in their outcomes, etc. It's a big issue. We are probably not the ones who will solve it immediately, but suffice to say that actually building an open source platform and open source models is not sufficient when we want to tackle real world problems. We need also to work on open data. Okay, and make sure that this data is correct, the data is clean, the data is reflects actually what can be measured in reality, etc. So this is one of the challenges we have in agent-based modeling, is that we of course rely too much on data. But if we want to tackle real world problems, we have no choice on this. Okay. So that's something to consider when you want to use agent-based modeling, is that not having the right data or not having enough data might actually threaten the use of your model at all. Even though your model is perfect and very nice and very interesting, if you don't have the possibility to access the right data set, it might be an issue. So in terms of platform, of course, Gamma has been free since 2006 and open source since 2008. Okay, and so you can find it on the link I'm providing here. I'm providing here. So it's a GitHub organization link. So you can find it here, and actually you can download it. We try to document it as much as possible so that it's very easy for people to download it in the developer version and use it on Eclipse. We use Eclipse as the main developer platform. It's a big system, so don't be afraid at first, but we welcome contributions. We welcome questions and comments on how the code is built and organized, etc. So do not hesitate if you are, I don't know, passionate about coding or passionate about modeling and coding, or you want to give a very interesting exercise to your students, do not hesitate to clone actually Gamma and to maybe to play with it a little bit, okay, or to copy it for your own purposes. Well, actually, I will not. Maybe we can talk about it later. This one, it's about the openness of data. Okay. Semantic supports. I don't have a lot of things to do on this, but it's the problem right now is that we produce a lot of models that we don't have very interesting systems to document them, and AI can probably be something very useful here. Actually, really saying what this model is really about. Okay, what kind of questions we are really tackling and how it connects to other questions. Okay. It's for the moment, it's quite fuzzy how we can reuse model easily when they have been built, even if you use the same platform. Okay. Because using the same platform or same language or whatever, it simply solves the syntactic problem. Okay, you have the same syntax, so it's of course easier. But the main issue is the semantic one. What does the model really talk about? Okay, how does it connect to other models, etc. And on that aspect, we are very close to a domain you maybe know, which is called the domain of ontologies. Okay, so more, we'll say more advanced way of representing knowledge. So ontologies, and maybe building an ontology-based library of models is probably the way to go. But for the moment, there is nothing like this existing. And after that, last point is really the scalability issues. Because the more ambitious the research questions, the larger the models and data sets you have to use. And when we have millions of agents, it doesn't work. Okay, it's too big. What's the point of a model if it takes more time than reality to simulate things? Okay, it's not possible to do it. So at some point, you need different things. So, for example, the possibility to summarize what is happening, and this is what we called surrogate models. Okay, surrogate models are models that look and learn actually of what is happening in a simulation, and they build a model out of it. And that's something which is becoming very popular. It's super interesting problem in AI. Okay, so how many simulations do you need to run so that your system learns how to replicate it without having to simulate millions of agents, for example? Okay, it's a very interesting problem in AI, very, very interesting. And one of the few ways, one of the domains in which, and I'm speaking on behalf of the whole Gamma community, etc., we are really willing to cooperate with people working on large data sets or AI techniques. So I will finish on this. Thank you so much for listening to me, actually. All these challenges, well, actually, it's open to anyone willing to contribute, okay? Maybe not only on Gamma, maybe using other things. I will be more than happy, actually, to answer your questions, but also maybe answer your mails as well. So do not hesitate to send me mails if you have questions popping up in the middle of the night in a few hours. So do not hesitate to send me a mail, and of course I will try to answer as soon as possible. if you want more information about the different things I've mentioned, like the simple project, Gamma, or the laboratory I'm heading across, do not hesitate also in visiting these different sites, right? And I will finish on this slide and give give the floor back to the moderator.
Thank you, Dr. Trugul, for your excellent presentations, especially with many examples regarding the multi-agent simulation and modeling. And you also already provide us the information regarding the challenges in developing the multi-agent-based modeling. And with that said, I'm sure we already have burning questions. So for the participants, if you have any questions or comments, please feel free to submit them via the Q&A box. And also for our viewers in YouTube, you could also submit your written question using the following format: name, affiliation, name of speaker, and questions. And then also, this announcement from the administrator, we have provided the attendance and feedback form. Please fill the form to acquire the certificates. With that reminders, let's move to our second presentations. It is my pleasure to introduce our next speaker, Mr. Andrea Arisal. Mr. Andrea is a researcher at the National Research and Innovation Agency, BRIN, where he is part of the Research Center for Data and Information Sciences. He brings extensive expertise in high-performance computing, distributed system, and big data analytics. He earned his Master of Engineering in Distributed Computing from the University of Melbourne, Australia, and completed his undergraduate studies in Informatics Engineering at the Institut Teknologi Bandung. With over 2 decades of professional experience, Mr. Arisal has played a key role in advancing Indonesia's computational research infrastructure. He currently serves as the Principal System Administrator of HPC Mahameru at BRIN, where he leads system optimization and benchmarking efforts. In addition, he is actively involved in academia as a research associate at the Center for Digital Innovation Studies and as an adjunct lecturer at the Faculty of Economic and Business, both at Pajajaran University. Prior to joining BRIN, he was a long-time researcher at the Research Center for Informatics under LIPI, and then his work spans a wide range of impactful applications, including HPC system optimization, disaster response planning and management system, as well as data management and analytics. So today we are delighted to have him share his knowledge and experience with us. So please join me in welcoming Mr. Andrea Arisal. Good morning, Pak Andrea. I'm sure you're ready with
Good
your
morning.
great presentation.
Good morning. Thank you for the kind introduction.
Okay, so without further ado, the screen is yours.
Okay, thank you very much for the kind introduction, and I really enjoyed the speak from Dr. Alexis, and I tried to modify my presentation and to update with based on your presentation, but I have not changed. But anyway, thank you very much, moderator, and good day for everyone. In this session, I would like to describe our ongoing research regarding multi-hazard evacuation, route optimization, and simulation for Indonesia disaster scenarios. This is a collaborative effort. Ideally, the idea is from my professor, Prof. Heru from University of Indonesia, and then I tried to collaborate with other people to do this to do this research. And I just got introduced Gamma a few months ago. So when we met, Dr. Alex and I met in Bangkok for Pragma, and we tried to create a small simulation. And then I tried to expand the simulation by accommodating the hazard optimization, hazard evacuation route from open data in Indonesia. The outline of this presentation would be the problem context and motivation, and after that, why we need that one, or the objectives, system architecture and pipeline, methodology, case studies and result, and simulation and conclusion. Why we need this one? Because Indonesia is high risk disaster nation. This is taken from Indeks Risiko Bencana Indonesia from National Disaster Management Agency, BNPB in Indonesia, and every part of Indonesia is already covered by red, especially in banjir, flooding, and there are many other disasters in Indonesia. So probably not a single piece of land in Indonesia is free from any disaster in Indonesia. So because of that, Indonesia is #1 of most disaster-prone country in Asia Pacific, and according to some report, there are more than 3,000 disaster events recorded per year, from scaling from small disaster like tiny earthquake that are usually happen somewhere in Western Sumatra, and to a very catastrophic disaster like few months ago at the end of the 2025, there were 3 provinces in Indonesia got flash flood and landslide, etc. And 274 million people in Indonesia exposed by multi-hazard risk. And how can we respond to that? There are various disaster happen in Indonesia, from volcanic eruption, earthquake, landslide, liquefaction, forest fire, flood, tsunami, flash flood, drought, and also compound disaster need to get the response, disaster response. However, the fastest evacuation route is not always the safest one. So, and the existing evacuation plans are often static, single hazard, and manual. It's already determined earlier, but never update. So we need to, how can we integrate the real-time information, multi-hazard scoring, and scalable algorithm to make an optimized route for Indonesia evacuation in complex terrain of Indonesia. The research objectives of this one is we are too lazy to collect data and to edit data manually, so we want to have an automated data extraction. We want to extract settlements, clusters, and evacuation shelters from OpenStreetMap, is open source data map data, and we use DBScan to cluster the housing complex. And then we also integrate the INARIS from National Disaster Management Agency hazard index, so we know where how the hazard index of this one place compared to another one. And then we want to have a multi-hazard graph model, so we can find where's the road networks that are less risk than other road, and where's the appropriate shelter for the evacuation. And then after that, we want to optimize the road computation, how we can find the best evacuation route, not only from the least weight using Dijkstra, but we also have to composite scoring function that where the hazard, where the route close to hazard zone or has higher risk should be avoided. And then we want to evaluate the optimized route, whether it's already good or there's another alternatives. And then we want to simulate by assigning population and shelter and how when many people walking on the road segment, there will be a congestion. So we need to also consider the congestion of the evacuation. In the system architecture, we create the 6 stage of processes. The first one is we want to extract data. As Alex mentioned, that data is real issues in agent-based modeling. So we need to have the up-to-date data and almost real data. So in this case, we want to have the latest information about the village roads and what are the possible shelters available in that hazard area. And then we take the risk score from Inaris BNPB using API, so we can enrich the data with the hazard risk index. And then we build graph building, and then make some routing, then assign the population to the village and simulate them how they can move from villages to shelters using the optimal routes, and then we output and simulate them the output using multi-agent based simulation. We consider there are some execution models like naive, sequential, parallel, using multiprocessing, and HPC using NPI distributed computing. So we can find where in which part of the process can be optimized and which part cannot be optimized. For example, the extraction, and we find that extraction and risk score collection is a bottleneck because we are using the public API that they have a limited request at a time. So we need to find a way to cache them, and then if there are too many file requests, it can be stopped and then resume again after the connection established and the response getting better. So and the data source, as I mentioned before, it comes from the OpenStreetMap. We take the road networks, nodes, age, and highway tags. So every road network has their own types that we can assume that number of population can walk on that road and how many speed of the walking there. And also we took the building footprints, and then we take using the DB-scan clustering to clusters to create a settlement cluster. This is important because we want to make the evacuation from settlement to shelters. Shelters, we decide the shelters we create shelters, assume shelters from the building text, from, for example, schools, most halls, hospitals, fields. There are public places and they can accommodate more many people, so we can assume there's shelters. And also we put admin boundaries to check whether in Indonesia there is level 8 and a level 9. Level 8 is kecamatan and level 9 is kelurahan. So we can make sure that every kelurahan or desa has some kind of at least small population. So based on building clusters and admin boundaries, we can estimate the population of the community in that area. Then we save the all into the forecasting. And also the second one is Inaris BNPB API. It is in Indonesia National Disaster Leaks. There are various layers: volcano, earthquake, landslide, flood, tsunami, flash flood, liquefaction, and forest fire, and etc. But we try to put them into, we download them per 1.1 kilometer square kilometer resolution and put them into the OpenStreetMap layer that we already download in previous slide. And then we also consider multi-hazard scoring if there are we will take some scenarios from historical disaster. There are multi-hazard disasters, so we can simulate them with multi-hazard scoring as well. And the batch casing, so we batch 20 on 40 requests, and it's one request. So it hopefully we get replies, but sometimes we got no replies or error replies, so we can stop and restart the request. And the third data is wilayah data. It's open source from someone Indonesian developer, and he created a PostgreSDB about L9 administration area with reference geometries, and also he created a CSV population for village and admin area and density-based estimation, so it can be used to estimate number of population in the cluster or L9 admin area. And for the settlement, we use the DB scan. So we take all the OpenStreetMap building footprints and cluster them by epsilon meter diameter. So when there are close, then we use 100 meters diameter epsilon. So house or buildings that close with diameter less than 100 meters will be included in one cluster. And then we compute the cluster centroid area, estimate the population. We can estimate the population of the cluster using area and of density, and also we can also use the population by building types. For example, it's configurable in the program configurable. For example, house, we put 4 person per house, or apartment 25, and etc. And then we snap the centroid to the nearest road node. So when it will be useful for the simulation, so every class settlement cluster will go through that road node. These are the configuration parameters and shelter geometry. And then after that, we try to use find the route, how to find a route from settlement to shelter. We use the two-stage algorithm. First is pathfinding. We take each village to run Dijkstra to our shelters and collect all the reachable path to the shelter. And then we score path routing. We score each path using composite route score, and then take the lowest score as a preferred route and select the few lowest score. And then we try to guarantee that at least one primary top routes and two alternative route should be available. And we try to relax the scoring. So if there is too high, we too low, we try to increase the risk. So every route is reachable from village to at least 3 routes to the nearest shelter. This road optimization, we find that road optimization could be parallelized. So we try to parallelize with trading. Then we try to trade with an worker. So it's also configurable. And then merge the result after completion. And pathfinding formula, we use the H-wide formula with each road segment. We measure the length of the road segment. The quality is the average quality. For example, one road segment could from one node to another node consists of several types of road types, and we can override them. And then we took the risk score using Inaris composite hazard score, and then we get the risk weight. And then for the path routing, we tried to measure the distance, distance divided by 500, and then average H risk and the works weight of quality, time, and distance of disaster from disaster, the initial disaster point. And we also put the population to shelter assignment. We run single pass. So with greedy assignment, we take the largest sheltermen and put them to the closest shelter. And then if the closest shelter is already full, and it will move to another shelter and then move to the fewer populated villages. And also we can use also linear programming with maximize total evacuation. For this one, I just used linproc from CP, and it's not really tested yet. Mainly for this, for now, we're still using greedy assignment only. And we created currently we created at least 10 scenario based on some latest disaster. For example, landslide in Banjar Negara. I took from the newspaper where's the landslide and take some information where it actually happened, and then extract the radius. And then after that, I simulate with the data core extraction, and we find that there are 1,000 villages, more than 1,000 settlements, and 31 shelters, and there are 10,000 road edges. And currently, the Inaris earthquake does not respond did not respond anything, so we cannot collect the Inaris hazard index for earthquake. So some earthquake simulation still cannot be run yet. And we tried the Merapi volcano with 15 kilometers, and because it close to the city, it has more than 95 road edges. So this could be the largest simulation, and I cannot run it. And it has millions population, so it cannot be run in my laptop. So the first case study is Negara's landslide. We extract 1,000 villages and 31 evacuation shelter and 131,000 population, and there are 5,000 candidate rows. There are 10,000 road edges, but based on the computation, we select 5,000 more routes from village to shelter. The scenario configuration, it is a landslide. It has 10 kilometers from epicenter. Hazard layer similarities. We use evacuation execution mode with full worker parallelization. And this is what we can collect from the OpenStreetMap, where we can see that there is the center of the disaster, and we collect the villages. The green are the building clusters, and the red one are the shelters. And also there are road networks. You cannot see that. And also we can see that this one is the 1 square kilometer hazard index, landslide hazard index taken from Inaris. And using the road optimization algorithm, we can find there are three major. There are one primary and two alternatives roads. The first one, the primary should be with the green one, and the secondary with yellow, and the tertiary is with the red one. Here, the more detail about the visualization, where these are the building clusters, and this is the road from the best route from the building cluster to this shelter. And for Merapi eruption, the simulation is the extracted data is really huge. So we can simulate. We assume that there will be, based on the population assignment, there will be 2.6 million population, and there will be 30,000 rows, road rows. So it could be difficult. Based on what we got from the road optimization, we tried to create a model, agent-based model for the disaster simulation. And the question is, does the following pre-optimized route perform better than other strategies in survival rate and evacuation time? And based on that question, we decompose agents, the population, villages, shelters, road, and hazard type. And we create 4 modes simulation. First mode is the naive one. Every population will go to the nearest shelter using road graph Dijkstra that's already included in Gamma. So we took that one, and then every population from village will go to the nearest shelter. And then the second mode that the population will see the hazard close to them, and then they will choose route that further away from the disaster. And then the third mode is the base route, that pre-compute route rank 1 only, and the mode 4 is random top routes. So if we have three optimal routes, so every agent can select 1, 2, or first, second, or third route per agent. There are other properties for the multi-agent simulation that we put hazard propagation. Hazard propagate from the epicenter to other area. Currently, we can only use circular only, so circular will expand, and then the second one is a shelter closure. Shelter that covered by hazard, it's already cannot accept any evacuees. We also create a BPR congestion model. So if there are too many evacuees in the same road segment, the speed of walking will be reduced significantly. And then hazard proximity penalty, where speed reduced linearly if they close to hazard zone. Capacity enforcement, when the shelter is already full with evacuees, the next evacuees should go to the nearest available shelter. And then we try to sweep the patch experiment. Here are the simulation. I will show the simulation later. And we can monitor the shelter occupancy, how the evacuation status, and how the evacuation outcome, how many survive and how many are affected by the disaster and how many still in transit. There you can see the some evacuees walking from a village to shelters. This is related works of this experiment is that several years ago, my professor has published some publication regarding to multi-objective routing, network routing generation. It's called responder. The previous studies using the shortest path only, and now this work with Jetstar privilege, and also there is integration. Previously, take pixel color from the Inaris map, because the current now we have Inaris API, we can take with API. And before the data collection using manually collected from the OpenStreetMap, and a point of interest identification handcrafted, and also the number of population is also handcrafted manually, but now the data collection and point identification is already automatic, but it also can be exported to a CSV, and then knowledgeable person, researchers can add manually. For example, in one village can put how many number of population in that village, or number where the shelters should be. It can be created also manually, can be added manually. And before it was a single hazard layer, but now we can have a composite hazard. And as been mentioned by Dr. Alexis before, I really had a great opportunity to have directly by the core developer, where we had fun coding in the one night. And at the time, we create, four of us created a hackathon, building a flash flood simulation. And then the same interface I still use now in current simulation. But we still have a limitation, like Inaris API limited it once request per second, so we cannot put many requesters at one time, otherwise it will be blocked. So and road network quality depends on OSM contributor coverage. So there are areas that has not been mapped in OpenStreetMap, so we cannot consider that one because we depends on OpenStreetMap. No real-time road closure and traffic integration, and use simplified agent, no household dynamics, and probably because I'm still new to Gamma, so it's still basic agent-based model. And population estimates using building types and density or area and density might be inaccurate for sparse area. So for example, in some village in Java, the area is really big, but the population is very sparse. No cross-village congestion coordination by pattern routing. But future works, we would like to complete all scenarios and try to create a comparative analysis based on various scenarios and based on the computing, distributed computing performance. Additionally, we need to add more routing algorithms, more advanced routing algorithm for large-scale scenario like MILP, star, etc. Multi-objective optimization, vulnerability weight routing, and multi-types agent-based modeling. Like probably we could introduce cars, bus, and etc. in the road network, how they will be affected the simulation. And parameter hazard propagation, like the simulation currently I still don't know how to simulate the flood, because flood should start from the river instead of a single point. And then how can we make the flood from river branch to the area close to those river branches. And in conclusion, this works currently provide full automatic open source platform for multi-hazard evacuation route from OSM and Inaris extraction to Gamma simulation. We use composite age weight route scoring formulation to determine the route where the optimal routes. Scalability currently with most than Badan Negara, and the Python port code can be executed using 10 parallel worker and to 2.6 million people. But in Gamma, I still not able to run it in Gamma. The Marapi scenario can still unable to run it Gamma, but I think I should consider to move into the non-visual simulation. I think it might be possible. Currently, we have 4 strategy. Probably we can have more in the future. And now I can show you the last simulation. Here's the simulation of we have evacuee agents, village agents, shelters, and road, where we put some behavior there, like congestion in road segment and how the behavior of evacuee. Anyway, we can start the evacuation simulation. We put it some scenarios. First scenario is near shelter, our evacuation, base route, and random top routes. And here's for the awareness. We can also people per agent. So currently there are every dot agent here is the 100 people, and the hazard speed and congestion models and what can be monitored. Now we can run it. And now we can find the group of people walking through the roads, and there the hazard expanding. Now there are some people affected by the road, by the hazards already still on the road. They're not safe yet, but some people already arrived in some shelters. They already survive. So, and we can see that at the beginning, some roads are decongested, and then it's slowly, gradually down. Some people already and now it's already ended because I limit the hazard max radius in only 5 kilometer radius, so it will stop in 4 kilometer radius. And we have, with the fourth scenario, random terrorists 47 already survive in the shelter, and 25% is affected by the hazards, 29% still in transit. Now, okay, now I can close the now, yeah. Thank you very much for the for listening to me, and thank you to Alexis for building the good tools for agent-based simulation like Gamma. Thank you.
Thank you, Pak Andrea, for your interesting presentation, including you also can see how Gamma works, how to say simulation works in Gamma, and maybe we should just go to the Q&A sessions. I believe there are already plenty of questions. Could the administrator show the questions? Okay, so the first three questions here are for Dr. Trogol. So would you like me to read, or could you just address to save some time, because I believe we have plenty of questions.
Yeah, no
So this is the
worries.
first three
Yeah.
questions.
So
Okay.
yeah, I've taken a little bit of time looking at the question before. So actually it's so the two first questions, I think it's a very valid and legit question. Actually, is that all this computational power we are using for building models, building AI tools that interpret models, etc., etc. Yes, they have an impact on the sustainable development. And whenever we need to build, yes, of course, data centers, cloud-based infrastructures, share the result of simulations, of course, we have an impact. And so there are a number of research on this. I don't myself personally work on this area, so I don't want to actually to talk about things I don't know very precisely. But I'm heading a laboratory where actually a lot of people are working on frugality and frugal systems. So being able to run things maybe with the same insights, but with less using less computational power, memory, or resources. It's not completely easy, and actually, it's for me, it's a philosophical question, which is it's not an engineering question. Okay, it's really a philosophical question. Should we use computational power right now to build such large models and run them? I have no definite answer to this. The only answer I can have is that, well, I better use the computational power and the data centers and network infrastructures to do this for sustainable issues than to build, I don't know, videos of cats fighting dogs or things like this. Okay. But I know it's not a very satisfactory answer, right? But yes, frugality, in a way, some part of it goes together with the last challenge I was mentioning, is the one on the scalability of these systems and the possibility actually to summarize a very complex model with simpler ones. Okay. Maybe there are, and no, actually there are some connections with the frugality of systems. So systems that don't use too many resources. Okay, so I don't know if I answered the question, but basically I can't give a very informed answer because I'm not an expert in this, but I have an opinion on this at least. Second batch of question is about so the relationship between ABM and digital twins. They come from two completely different worlds. Okay, so digital twins initially was mainly to have a complete and very accurate representation of the physical, mostly physical actually representation of, for example, a city. Okay, so with electricity, with all the circuits, all the fluids, water networks, etc., etc. Now it has become the meaning actually has broadened a lot, and it has become we use sometimes digital twins for situations where it has nothing to do with electrical networks or water networks or whatever, and actually where we accept that the accuracy of the representation extends to human beings. Okay, and in that case, we are very close to agent-based models, very, very close. And Gamma, I know, is being used in Vietnam, for example, by colleagues, and I think one of them is in the room listening to me actually at the same time, me. We use actually Gamma as a foundation for building, for example, digital twins of cities. Okay. There is one point, however, where again I'd like to warn a little bit people. I already said it twice during my presentation. I will say it 3 times. I will say it 3 times. It's that behind the digital twin approach, there is this kind of fantasy that you can completely replicate a system. Okay, so you build a model of a system. But I insist on this, and I think it's quite important. There is no such thing as a model of a system. You see the system with different viewpoints based on questions you have. Okay, and the main difference for me is that when we build an agent-based model, we build it to answer a question, a very specific question. Sometimes the question when people want to build digital twins, actually they don't have questions. Just have to have a replica of the thing, and the thing is that it's not completely true. They have questions, but you pretend that the system is completely accurate, but you forget actually to model a number of its components, usually human beings. So both approaches are very complementary. Agent-based modeling can be used to build digital twins without any issues, without any problem. It's more and more used in that direction, and probably the 2 terms at some point will be exchangeable. I mean, we will use them in a completely equivalent way to designate quite accurate models. But again, I really insist on the importance of keeping in mind that models answer questions. Okay, they are not the reality, and they are not here to just represent reality. The environment actually can be an agent by itself, okay? Or it can be a set of agents. It can be a network of agents. It can be, so what we call environment is really just a convention, okay? So we agree as modelers to say, okay, this is part of the environment, this is part of the agents. And sometimes, for example, in many simulations, what we call environment in the simulation is just a database in which agents are picking up some variables or attributes, okay? And it's okay. I mean, we don't need to have very accurate geographical information systems if the question is not about moving or things like this. Okay, so there is no real definition of what the environment should be or is. And regarding the relationship with LLMs and ABMs, of course, there are a lot of relations. So a very obvious one on which we are already working actually in Gamma. There are many ones, many different ones. I will only quote two of them, one of which is already integrated in the next version of Gamma, which is supposed to be released sometime in June. Okay. So first, using LLMs to build more realistic social agents. Okay, that's very easy actually to script agents using LLM. So they can have a very rich behavior, they can have very rich interactions, etc., etc. So that's something that is already done in many different social simulations. There are two things to consider, however. One is that, of course, you have, well, it takes a lot of power, computational power to do it. It depends if you do it online or offline, etc., etc. But basically, it's most costly than just having a set of programs or rules to govern the agents. But it's richer, and maybe it can be interesting, for example, in participatory models, where you want to have people play the same, play in the same or equivalent models, but not exactly the same. Okay, so you want to have a little bit of surprise every time or changes. Second warning about this is that if you begin to use LLMs in a model, you lose all the qualities of reproducibility. Okay, and that's an issue in some places when you want to explore models. Actually, you can't reproduce a model based on LLMs. Okay, because usually they are here to provide different new original answers, and also because we don't know how they really work. Okay, and so this opacity goes against the transparency that we try to promote. So that's a second warning. But again, sometimes it's very, very convincing and interesting in participatory setups, okay, to have LLM-based agents. And the second use of LLMs is to build a complete model. Okay, so instead of having to learn a language, to learn protocols, to learn different things, sometimes it's really complicated for people who come from social science or other non-computer science to have to build, to completely build the program, actually, to have something running on their computer. There have been in the last years a lot of I don't know, proposals in terms of, for example, graphical modeling. So you just assemble different boxes and you put arrows, and it will provide you with a running model. But even that is, most of the people, if they don't know how to do it in the first place, they will not want to learn different languages to be able to write a model. So in that respect, LLMs can provide a very interesting way of building a first model. Okay, so you prompt your model, And this is something we are already now doing. Actually, the next version of Gamma will come with a Copilot plugin. So you have Copilot running in Gamma directly, and you just say, okay, well, actually, I will not do it because I'm in the development of Gamma, and probably it will not work. But actually, I've already tested it, and it works very well. You write something like, I have this kind of data, so you provide the data, and you say, okay, I would like a model answering the question of how should people move, blah 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 blah. Okay, let's say 5, 6 lines of prompts with all the required details, and Gamma will build the model for you. And of course, provide you with hooks. And this is what I'm working on right now, is that the hooks are a little bit realistic and interesting, saying, okay, here we need to have a little bit more insights. Here we need to have more accurate behaviors. Here we need to have this and this. But the good point is that the model, the skeleton of the model is very good for the moment. And it improves actually every time we use it. And it's documented. So there is a full documentation coming in. So that's the two main connections I see between ABM and LLMs. But I'm sure there are many others, and I'm definitely very, very, well, a little bit fascinated sometimes by this new technology and how it simplifies the modeling part and maybe tomorrow the exploration part. Okay, probably using AI could be quite. Okay, so the last question, and I will finish it. I don't know, actually, exactly. I don't know. I don't know which technology you're talking about exactly in managing the development of the sparkly islands in South China Sea. I probably am not skilled enough in geopolitics to be able to give a good answer to this question. But of course, everyone can use the technology. Okay, there is no, I mean, no limits and nothing. So yeah, it's perfectly possible that some people use it, and but I'm sure actually anyone can use it to drive development. Okay. So I will maybe finish on this.
Okay, thank you for your answer, Dr. Drogo. I believe there are no follow-up questions from Dr. Asril and Pak Agung Santosa and Pak Muhtamar Ahmad, yeah. And I suppose if there are any, Dr. Drogo would be happy if you send your questions directly. Okay, there are still 2 more questions in the slide. There are also raised hand questions, but it will be addressed after these slide questions. Okay, the first question is for Pak Andrea. The first in this slide is for Pak Andrea to the question. So please, Pak Andrea, the time is yours.
Okay, thank you, Wahyu Widiasi. How does the concept of okay, probably I not really understand about the question, but regarding to the archival integrity, the from the extraction, OpenStreetMap extraction and the hazard collection from OSM and NARIS, it can be casing and can be redirect to CSV and JSON output. So in order to evaluate and update the data, people, for example, the stakeholder can update, for example, the building settlement, building cluster that create a settlement, we put the approximate number of population in that cluster. And then if someone who responsible and have know more about number of the population in that area, they can directly update the data, and then we can use the input into the simulation. And also we can the automatic part of the OSM extraction is also extract some buildings type into the shelter. So they assume that these buildings type can be used as a shelter in case the responsible can know that there are more appropriate location of shelter. They can insert and create a additional shelter with the geographical location and the number of capacity to the shelter, and it can be used in the simulation again. I hope I answered your question. Now, the second one from Mukhtar Ahmad. Does the pattern of pathfinding and pathrouting depend on local wisdom? Unfortunately, no. No, it's completely based on the data available, and so we can. I don't know. I don't have hook for that one. Local wisdom. So it's better to go to this way instead of the other way. It's not implemented in the code yet. Probably I need to, because this is an early stage of research, so we haven't discussed with stakeholders. We plan to discuss with the stakeholders in a couple of months, but currently we try to complete the data collection and path funding first, and then also present this result to the stakeholders. I also have some question to me from the question and answer from Pak Hasril. Should the simulation development involve policymakers such as National Disaster Management Agency to ensure alignment? Obviously, yes. We, as I mentioned, we will discuss with the Disaster Management Agency in a couple of months. And should they, as an authority entity, can be an agent in the simulation using Gamma platform? Yes, it's also one of the plan that the previous publication from my professor that it's also includes how we arrange the what is it? The disaster response team allocation, where they should be allocated, they should be positioned, and how they can be moved from one shelter to another shelter. It could be another agent like response team, and we can put them. We can have some place where they are originated, and then when disaster happen, they can go to which shelter is the best route for them, and how we can allocate them, schedule their routes as well in the simulation. It could be. It's also another plan for in agent-based modeling simulation. So, thank you. That's all.
Okay, thank you, Pak Andrea. I think we still have a quick question, maybe for from Pak Yuyun, yeah. The hand raise from the hand raise, yeah. Okay, Pak Yuyun, please.
Baik,
Deliver
thank you. Thank you, Bu Husnul, for your time. Dear Dr. Alexis, nice to meet you. And hi, Dr. Andrea. Thank you for your insightful presentation. So, I am not a researcher in this field, so I am trying to understand your point. In your study, you saw how to build model that that represents real world phenomena through simulation. So I saw your presentation. You propose agent-based modeling to simulate this. So, however, in the reality, there are many complex situations and many factors to consider. In my opinion, it can be quite challenging to collect the real data and evaluate the simulation. So my question is, how the strategy to collect the data that represents of real world condition, and how the model validate, I means for your simulation, and then how to validate to ensure that this simulation result truly reflect real world phenomena. This is the question for the Dr. Alexis. And the next question for Dr. Andrea. Also, thank you for your insight presentation. So I saw your presentation. Maybe your topic is about multi-hazard evacuation simulation. Also, I saw your presentation. You use distract algorithm. In my opinion, maybe you use the algorithm to the scenario how to optimize the road. Okay? You propose for strategy and you use multi-agent evaluation simulation. Your strategy to find short paths, hazard aware routing, best route, and others. So, in my question, how to validate and evaluate your model to ensure that simulation results truly reflect real-world application. So I don't know the simulation need evaluation or not. So I would like to learn more about it. Thank you.
Okay, thank you. Maybe I will begin with answer to the first questions. So thanks a lot for your questions. Actually, the question of the relation between model data and of course the realism
Evaluation.
of simulations is quite. I mean, it's a central question because for me, what we call data is already a model. Okay, so actually data does not exist in the world. Okay, we decide to extract data or to measure data or to build information from data, but it's already a model. It's already we already choose to focus our attention to this and this and this. So maybe it can be the age of people, maybe when you have a population, maybe it can be the behavior of people, you want to have surveys, etc. But so for me, what we call data does not exist without models. Okay. It's because we already have a model of the world that we are collecting these and these and these data. And so what is important in that case is that the data we are collecting is related to a question. So for example, if I have a model with people, I will not represent all the complexity of a real person because it's infinite. Okay, I could go to infinite dimensions. Okay, one person is so diverse. You have so diverse indicators, so diverse variables to represent it. So, okay, so many attributes. So it means that the data we are collecting is a data which is strongly constrained by the question we are interested in. So whenever, for example, I have people driving vehicles in a simulation of traffic, I am only interested in their driving behavior. Okay, and maybe driving habits and maybe driving preferences. And maybe I will be interested by their age and the relationship between this age and their reflexes, how well they still drive, etc. But that's all. And for me, a person in that model will be very poor, actually, compared to what social sciences can consider. Okay, it will be just a set of attributes that I am interested in. So that's the first thing, is that there is a strong relationship between the question in your model and the data you are going to collect, or the data you are going to rely upon. And sometimes this relation is so strong that it is the reverse. It is because you have some data you don't understand that you build the model. Okay, and you build a model to understand your data. So they are very strongly interconnected. And after that, so once we build the model, etc., how do we assess the link, I don't know, the realism of the model? Okay, for example, how do we assess that the model is viable, is relevant to answer our questions? So first of all, there is again this question, this issue of a question. Okay, there is a question here, and so a model will be relevant with respect to a question, but maybe it will be completely irrelevant for something else. Okay, and it's okay. And the third thing is that to do that, we have quite, I would say, formalized protocols. So the first one is sensitivity analysis. So make sure that what we have in terms of data, I mean, what is really important in terms of data, because some of the data maybe you might have is absolutely not relevant to answering your question. Okay, it doesn't change the outcomes of the model, for example. Okay, or things like this. So sensitivity analysis, there are methods to do it, and methods to explore your model and understand the relation between the data and the model. Then you have the calibration. Calibration is usually it's running your model against past data. So data you have collected in the past, okay, in existing occurrences of the system in reality. So it's real data we have collected in the past. And the good news is that actually you can use the same indicators in your model. Because in my model, I have, for example, in the model of traffic, I have people, I have vehicles, I have roads, they are simplified. But basically, I can study them and measure them exactly the way I measure things in reality. Okay, I can measure the speed of vehicles, I can measure the degradation of roads, I can measure, I don't know, the fatigue of people or whatever. So calibration is really making sure that your model, at least on past data, is valid. Okay, is okay. You obtain similar or statistically similar outputs from the same inputs. Okay. And the last one is validation. And validation, actually, it's almost the same, but against data that you don't know yet. So it's data that we are measuring while we are running the model, or maybe we have made a prediction with the model and we try to see how valid this prediction is. So this one is complicated because sometimes your model is about things that will uncover in 30 years. Okay. So of course we don't have the data, so it's complicated. And for that, what we use in the, let's say, scientific modeling community, sometimes we use a series of models. Okay, models built using different techniques. This is what they use in the IPCC, for example. They have thousands of different models and they try to understand. So of course they don't take the average, it will be too simple, but they try to understand whether these different models are valid with respect to one another. Okay, so in 30 years, if they all converge to the same results with very different hypotheses and very different inputs, probably it means something in terms of the validity of the model. Okay, so I hope I answered your questions, but that's
Okay, thank you, Mr.
you're
Alexis.
welcome.
Regarding to your question, actually, I don't have the answer. It's probably partly already answered by Dr. Alexis, but to answer, it's quite complicated, and currently I have no answer how to validate the model and the result of the model. Yeah, we plan to discuss with stakeholders about the output of this research, and then we try to reiterate how the input of the stakeholders, and we try to accommodate in our modeling and simulation. That's probably
Thank you,
the.
Mr. Andrea. Thank you.
Thank you.
Okay, thank you, Dr. Drogo and Pak Andrea. Due to the time limitations, we apologize if we cannot are unable to address all the questions. We appreciate the active participation from all the participation here in Zoom and all the viewers via YouTube streaming. And of course, to Dr. Drogo and Pak Andrea for your response that covered all the questions raised here. And as a conclusion remark, we have discussed in this webinar the importance and the relevance of multi-agent-based modeling to study complex and dynamic phenomena through imaging patterns in variety of domain problems such as health and disaster, among others, as the outcomes of using multi-agent-based modeling, we could better understanding of system dynamics, identification of unintended effects, and more informed decision making. And with this remark, I will give the screen back to Ms. Christine as the MC. Thank you again, Dr. Drogo and Pak Andrea.
Thank you so much for your moderation. It was very nice.
Okay. Thank you very much to moderator Dr. Husnul, all speaker Dr. Alexis and Mr. Andrea, and all participants. Now, next agenda closing remark by Head of Research Center for Data and Information Science BRIN, Professor Dr. Esa Prakasa. To Professor Esa, the screen is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen, distinguished speakers, colleagues, and participants. As we conclude today's webinar entitled Simulating the Future Multi-Agent System for Complex Socio-Environmental Dynamics, on behalf of the Research Center for Data Information Sciences, BRIN, I would like to express my deepest gratitude to everyone who participated and made today's webinar possible. We have spent the last few hours exploring how multi-agent system and the Gamma platform allow us to move beyond traditional modeling to capture the adaptive, decentralized behaviors of our world. Today, we gain invaluable insights into the theoretical foundation and practical application of this system from two respected speakers. Firstly, Dr. Alexis Drogo. As an inventor of Gamma platform, he has provided a comprehensive look at modeling complex socio-environmental system using the Gamma platform. And then secondly, Mr. Andrea Rizal has demonstrated the multi-hazard evacuation route optimization and simulation, especially for Indonesian disaster scenarios. In this webinar, our objective was not only to share the knowledge, but also to foster collaboration across computational modeling, disaster risk reduction, and urban planning. The engagement during our discussion session can initiate a strong collaboration in the near future. Lastly, Once again, thank you to Dr. Alexis Dargul and Mr. Andre Arizal for inspiring presentation, and also Dr. Husnul Khotimah for moderating the session, Professor Budi Prawara, the Chairman of Research Organization for Electronics and Informatics BRIN, for supporting this event, and also the organizer team and all of the participants for your contributions and attention. We look forward to seeing you in the future SDI DESAIN webinars. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Okay, it's now time to announce the 3 lucky winners. Okay, the winners are congratulations to the winners Agastya Pandu Satria Utama, Septi Nurul Aini, and Raka Putra Ristianto. We kindly ask the winner to contact Miss Tiara or direct message the PRSDI Instagram account. Congratulations. Okay, distinguished ladies and gentlemen, we have now to the end of webinar. On behalf of the organizing committee, we thank you for your presence and participation in this webinar. I would also like to remind all participants to complete the attendance form that has been shared at chat Zoom and YouTube. We sincerely hope this webinar will expand our knowledge and provide valuable insight for all of us. I am Christine. It's been a pleasure to be your host. Wassalamualaikum warahmatullahi wabarakatuh. Thank you. Have a pleasant day and see you again in the next webinar. Thank you.
Thank you.
Thank you all. Thanks again for inviting me. Bye.
Thank you.
Thank you.
Thank you, Dr. Alexis.
Thank you very much.
Thank you everyone. Permission to end meeting. Assalamualaikum warahmatullahi wabarakatuh.